Alright, so continuing with direct proofs, we want to make a claim here, and it's a little bit different than previously. So we're going to let x be an integer, and our statement's going to say if 5x minus 7 is odd, then 9x plus 4 is even. Alright, so we want to do a sketch of the proof, and that's because we don't really know what direction to go. So naturally we're going to think that if 5x minus 7 is odd, we could write it as 2k plus 1, but notice now that we have an x and a k, and things are going to get kind of weird, especially if we try to find something like x. It's going to be some rational number. Definitely not an integer. Try to focus on x and how it's going to be related to 5x minus 7. So what does it take to make 5x minus 7 odd? Because we know that's the assumption. It's got to be true. If we plug in 2, it's true. 3? Not true. If we plug in 4, it's going to be true. It's odd. And if we plug in 5, it's not going to be true. So a starting point here might be that we know x has to be even in order for 5x minus 7 to be odd. So what we can do is develop a small theorem, a lemma we'll call it, and we can use that inside of our proof to prove this bigger statement that we're trying to prove. So lemmas are pretty much the same thing as theorems. It's just that they are useful within a specific proof. So if I use a theorem to prove a theorem, I could call that first one a lemma if it's in the context of a proof that's proving the second theorem. Alright, so we can think of it as just something to help us along the way that's not a definition, and it's not necessarily a theorem. Typically we think of theorems as these really powerful statements or results. And so, for example, we might have a lemma, a definition, another lemma, two definitions, and then another lemma. And when we piece all of those together, we end up with the theorem. Something more powerful than the lemmas. Alright, so let's try to prove the original statement. We're going to assume x is an integer. And before we even mess with the statement itself, we're going to state our lemma and prove that. So our lemma is if 5x minus 7 is odd, then x is even. And remember, we can prove that using the contrapositive. If we try to direct proof on this, it's not going to work out very nicely. Alright, so if we want to state the contrapositive, if x is odd, then 5x minus 7 is even. So remember, it negates those two and flips them, the p and the q. So really odd means not even, and even means not odd. So let's do a direct proof on this contrapositive. We're going to assume x is odd. That means it can be written as 2 times an integer plus 1. So we'll say 2k plus 1. Alright, so this is pretty simple. 5x minus 7 we can rewrite as 5 times 2k plus 1 minus 7. And that's really going to be 10k plus 5 minus 7, so 10k minus 2. And then we can factor out a 2, and so we're going to have 2 times 5k minus 1, which we can really just say is 2 times an integer. And since 5k minus 1 is an integer, we can call it something like q. So we wrote 5x minus 7 as 2 times q, some integer q. And so we're done, at least the lemma. Alright, so back to the proof. We're going to assume x is an integer, and we're going to assume that 5x minus 7 is odd. So by our lemma, we know that x must be even. We've proved it. So that means that x can be written as 2 times some integer. We'll call it m. And so if we look at 9x plus 4, we can write that as 9 times 2m plus 4. And so when we simplify this, we end up with 2 times 9m plus 2, which is really 2 times an integer z, which means that 9x plus 4 is even. And so we're done. So we'll put the statement here and our tombstone at the end, and we're done. Alright, so we have a result here. X squared is even if and only if x is even. So remember that this thing is a biconditional statement. If and only if. And if you remember how that's defined, what we did in logic, if we say p if and only if q, that's really the same thing as if p then q, and if q then p. So we have two things to prove here. We have to prove a forward direction and the backwards direction in order to show that this thing is true. So the first one listed here, if x squared is even, then x is even. We can prove that using the contrapositive. And remember, that's going to be the forward direction, basically just the conditional that we're using. The second one, we can just use a direct proof on what we have there. And I'm going to put a forward arrow on the first one to show that we're going forward, and then backwards for the second one. So we'll start by proving the forward direction. Since this is a contrapositive, we're going to assume that x is odd and then show that x squared is odd. And so if we assume x is odd, then we can write it as 2k plus 1. And so when we look at x squared, we're just going to replace x with 2k plus 1. Okay, so if we expand this, we can factor out a 2 just from the first two terms, and then we have a 1 left over. So we have 2 times some integer plus 1. And by closure, that thing is an integer. So we could call this 2l plus 1. Alright, so for the backward direction, meaning the converse, we're going to assume x is even and then show that x squared is even. And we've done something like this before. X is going to be 2k, and then when we square it, we just get 2 times some other integer. Alright, so we'll call that other integer r, and so we have 2 times r. And that is the proof for the converse, and so we're done, the second part. So now that means that we've proved the biconditional statement. That is, that we've proved x squared is even if and only if x is even.